All right, welcome to CSRF 101. My name's Aaron Bishop. I'm a principal penetration tester at Security Metrics. I've been a penetration tester for about 6 years. Before that, I was a developer for a couple years, and then I did DevOps and IT type stuff for a couple years before that as well. So I've been involved in the security realm for a little over a decade now. And one of the issues that I've come across pretty frequently is Cross Site Request Forgery, also known by its acronym CSRF. Some people also call it XSRF. Doesn't roll off the tongue quite as well as CSRF. Other people refer to it as session writing. So if you're here, hopefully you're here to learn about CSRF, or you're here because you want it to be closer to the lunch lines out here. Just right out these doors to the side. We're going right up to lunchtime. I'm going to try and get out a minute or two early so you can just, first ones in line. They're right out there. So let's go ahead and just dive right into cross-site request forgery and what it actually is. So generally, people go to OWASP for definitions and to learn a little bit more about vulnerabilities. But a lot of people, even after reading OWASP's definition of what cross-site request forgery is, aren't entirely sure of what's going on. It's kind of hard to really explain it. I've tried a few times, but the best that I've been able to come up with is you're essentially tricking a user into performing an action they didn't intend to perform. Doesn't involve anything complex. You don't need to have any special privileges or access. You don't need to have man in the middle or anything. You just get a user to perform an action they didn't intend to perform. So we're going to go ahead. The easiest way I found to kind of grasp it is to actually take a look at what is actually going on in a CSRF attack. So we're going to follow our fictitious user Bob here. He's happy to be a volunteer. He's waving to you guys. And see what would take place in a typical CSRF attack. So here we're taking a look at Bob's desktop. He's got just a couple browsers windows open. Bob has the thing for unicorns here. Then over here on the right, this is a tool that's known as Burp. We commonly use it as pen testers. Maybe some of your developers may use it as well. I'm using it just as a proxy to capture the requests that are coming from Bob's browser. It's not going to be doing anything special. It's just capturing every request that Bob's browser sends out so we can see what Bob is actually doing. So Bob goes ahead and comes to this site, and not that site. It's known as Burp, or the Burp Suite. You can find, I believe their website is portswigger.net or .com. They have a free community edition if you want to check it out yourself. And so Bob here comes to safe.com. And fair warning, if you're trying to follow along on your laptop, safe.com is owned by somebody, so this isn't actually safe.com. If you start playing around on safe.com, you probably don't have permission to. They might get mad. So don't try and follow along with safe.com or the other site that'll come up, not evil.com. So in this instance, Bob goes to safe.com, gets his username and password, and logs in. And it brings us to Bob's little profile here. Maybe Bob had an awesome night playing Fortnite, feeling really good about himself, and just stoked and decides to go ahead and change his name to King Bob. And so he changes his name to King Bob, and now everybody knows that he's feeling awesome and had a great day, and that's all he can really do. If we check over here with Burp, we can see the request Bob sent. It was just a simple post request to safe.com that contained in the body of the request his new name, which was King Bob. And so Bob, feeling really good about himself, goes down to one of his favorite sites just to get a little background music, a little something going in the background to distract him if he gets kind of locked in thought. And so he goes to his favorite site, notevil.com, which, as we see, ends up changing his name up top to CSRF. It just starts up his favorite little video to distract him. So we also check back over here in Burp here. We can see Bob went to notevil.com, and then right after that, there was a request from Bob's browser to that profile page to change his name to to CSRF. And so that is the most simple form of a CSRF attack. We'll step back and actually look at what happened. So if we walk through what happened in this attack, we have Bob here that went and visited safe.com. So he logged into safe.com, and safe.com recognized his username and password and set a cookie to identify Bob's session. And so Bob's browser had that cookie and stored it, and so all future requests for safe.com would include that session cookie. So afterwards, Bob then visited notevil.com, and hidden on the page of notevil.com was a malicious script that whenever a user visited notevil.com, that script would execute. And that script was just a simple request to change the username of whoever visited notevil.com. So in Bob's case, he visited it, the script executed, and it resulted in a post request to change his name to CSRF. And then as part of it for it to be a CSRF attack, it included Bob's session cookie. Because Bob's browser, it's just the nature of the browser to include the cookies that are associated with a domain that it has stored. So I want you to stop and think for a minute about the functionality that your site performs. Maybe you don't do much besides handling usernames, maybe passwords. If it's something more serious like banking institution or some other sort of financial institution, if these requests aren't protected, they can be exploited using a CSRF type attack, and users can unintentionally perform these actions, which maybe they transfer money, maybe they change their password. Some instances that I've come across, there was one instance of a company that I was testing where they handled bills. You could pay your different utility bills. I think they handled credit card bills as well. But there was an option that their agents in the company could just approve or verify that a bill was paid. And it was vulnerable to CSRF, so any user that they could be tricked into verifying that another user or that a user's bill had been paid, even if it hadn't been paid. So free bills. One of my colleagues discovered an instance where it was for a daycare type facility where you could change the PIN that was necessary to check out kids from daycare, which is kind of a scary possible attack to possibly take other people's kids. Another attack that I came across that I thought was pretty nice or handy was a pizza delivery place. And it was kind of a multi-stage CSRF because you could change the delivery address and then submit an order. And so I had it set up that if anybody visited my site, they'd submit an order to the site and I'd get free cheesy bread and Mountain Dew. And would have been pretty awesome, but I'm not a malicious person, so it didn't actually pay off for me at all. Now, CSRF isn't a new attack. It's been around essentially since the dawn of the internet, back when GeoCity sites ruled the web and there wasn't anything cool to really look at. But a notable example that has taken place is known as the goat worm. It kind of took place on Twitter, platform that many of you may be familiar with. I personally don't use Twitter, never saw the need, but there's this notable attack, the goat worm, that took place on Twitter. And so what happened was there was an initial user that sent out a malicious link. They sent out a tweet that said, "I love to perform explicit acts with goats." And then they sent out a malicious link and they tweeted it out. So any of their followers that clicked the link to see what was going on with this tweet would also be victims of this CSRF attack. And so because of it, they sent out the link, and then they went out to their followers, and their followers, when they clicked on it, they then tweeted out the same link to their users or their followers. And then they clicked on the link and spread to their followers. And in roughly 2 or 3 days, it had spread through 70,000 plus users of Twitter. just victims of the CSRF attack, where everybody was tweeting out that they love to perform explicit acts with goats, and then a link for everybody else to click, and it just kept spreading and spreading and spreading. And because of attack, like this attack wasn't very malicious, maybe kind of annoying, didn't perform any terribly damaging activity. Nobody lost any financial data or anything. It just was a malicious link, and users, without knowing it, performed the action of tweeting out the link. In Bob's case, his username's changed, also not very malicious. But there are malicious instances out there, which is why, for a long time, CSRF topped the list in OWASP. It originally made its appearance in 2007, and it was number 5 on the OWASP top 10 list. Held the position of number 5 also in 2010. 2013, it dropped a little bit, and most recently, OWASP decided to remove CSRF from its top 10 list, with its justification being that because of modern frameworks, CSRF isn't as prevalent of an issue. The OWASP community said that they're only seeing it in maybe 5% of web applications that they're testing or examining. I disagree with that. Most of my colleagues would as well. I see CSRF in about 50% of the web applications that I test. And the ones that aren't vulnerable to CSRF are generally ones we've tested in the past, and we've flagged them for it and told them, hey, you guys need to fix this, this is an issue. I see a lot of instances of people that might assume they're safe in some way, shape, or form, but they're not. They haven't actually taken the steps necessary to protect themselves. Protecting yourself from CSRF is a fairly simple activity. We're going to take a look at that to show you just how easy it might be. And we're going to go back to the scenario with our buddy Bob here. And these are the steps that we kind of already went through with Bob visiting notevil.com and that malicious page, or the malicious script being rendered. So let's pop back over to our buddy Bob. So Bob, maybe he got annoyed because he couldn't keep his username King Bob, and it kept changing whenever he would try and go check out his cool unicorn video down there. Told the developers something funny was going on, so the developers looked into it, identified it as CSRF, and implemented a fix. They updated their site and they told all their users about it. So now Bob goes, logs into the site again. Everything stays the same, no difference for Bob. The only thing that's different is he has this nice new banner that says, the site's now equipped with CSRF protection. So Bob changes his username to King Bob. And once again goes back to start up his cool unicorn video. So he kicks it off, and his username stays the same. It doesn't change this time. The attack was foiled. But if we look at the requests that were sent, once again, Bob went to notevil.com, and Bob's browser then attempted to make a post to safe.com that had the body of CSRF. The difference here being that this time the server responded and said it was an invalid CSRF token. And if we look at the request that Bob sent to actually change his username, this time Bob sent the request with his username, and then included in the request there's a giant token. It's a randomly generated string that would be next to impossible to try and brute force it within a reasonable amount of time. That identified that Bob intended to perform that request. So that token, a CSRF token that gets sent, a lot of times it's referred to as a synchronizer token. The token being unique per session. So every time Bob logs in, he receives a new CSRF token. And ideally, sessions are kept short enough or they expire soon enough that that token doesn't persist for an extended period of time, reducing the window for possible brute force. That's a large value, and most importantly, if the token isn't valid or if it's not included, then it's just rejected. I've seen it a lot of times where people assume, hey, we're including a CSRF token in our request, we're safe from CSRF, right? But if you remove the token, the request still succeeds. They're not actually validating that it's a real token on the server. So it's not providing any protection. It's just some arbitrary parameter that's included in the request. It needs to be verified on the server side that that was the correct token that was included, that Bob did intend to make that request. Another possible futuristic protection, there's a same site attribute that is available for cookies. It's not widely supported, doesn't provide full coverage yet. I think it provides about 70% coverage. That somewhere down the road it may be the way to protect users against CSRF attacks. So it may be worthwhile to enable it now if you don't currently have it enabled, but I want to rely on it as your sole means for CSRF protection. If we look at the example that we've been following with our buddy Bob here, the session cookie that Bob has and actually uses has a same site cookie or a same site attribute applied to his cookies. But my version of Firefox that I'm using doesn't recognize that attribute. It's just ignored, so it's not providing any form of protection. Somewhere down the road, maybe that will be the way to protect against CSRF attacks. But right now, including something like a token in requests is an easy, surefire way to protect against CSRF attacks. Other options, that's a nice passive way. Your users don't even realize it's going on. It's just happening in the background. If it's a more sensitive request, you can use something that's a little more active, such as like a CAPTCHA or having the user re-enter their password. Yeah. So those are really your two options for CSRF protection, either a passive method, such as including a CSRF token, or maybe a header with a unique token inside of it, or you can go with active protection, where you're having the user interact with the website either by re-entering their password or by filling out a CAPTCHA, something that would identify that that user is actually intending to perform the action that's taking place. So those methods of CSRF protection have been known for years and years and years, all the way back to earliest paper I found about CSRF attacks was back in 2003. They were referring to it as session writing in that paper, but their recommended practice was to include a token to protect requests. And so with modern applications, though, we've been moving towards single-page applications, which primarily use JSON to pass around application-related data. And so a lot of developers have had a false sense of security because using JSON provides false protection, I guess you could call it. And I'll show you what I mean here. So in this example, we're going to say Bob's developers decided to update to use a newer modern framework. Maybe they're using Node with Express or Angular or something like that. JavaScript type framework that is primarily using JSON to pass around application-related data. So when Bob goes to log into the application or changes password, we see a nice little JSON object that's passed instead of just a typical name equals, it's now JSON. And so when our attacker tries to mimic that behavior and send JSON, his request is blocked, and he gets an options request the browser sends an options, and the request just dies there. So CSRF didn't take place. So from what I've seen, a lot of developers assume that since that's taking place, they're now safe from CSRF. The attacks, in their mind, been mitigated. It's not going forward. It's just stopping at that options request. They're not allowing credentials to be sent, and so they're safe, no problems. We take a look at Bob's request. He sends the JSON. NotEvil.com tries to mimic that behavior by sending the JSON and the credentials, which results in Bob's browser sending an options. And it just dies there. It doesn't continue any further. The Problem being that options request is being triggered by a specification that came out a few years ago that's known as cross-origin resource sharing, or since we love acronyms, it's commonly referred to as CORS. CORS was a specification that kind of spelled out how websites should share data amongst each other or make resources available. And CORS said that non-simple requests require a pre-flight. That's what that options request was. It was a pre-flight that was spelt out by the CORS specification. Essentially, Bob's browser was checking to see if the website supported the request to send a JSON that was initiated by an external site. So simple requests, those are a lot easier to define than trying to define all the various ways that a request is non-simple. You can think of it as just the ordinary requests that have been around on the internet for forever. That's just a GET or a POST with a standard, essentially the standard HTML form being submitted to a page. So if you want to just get an image from a site, that's a simple request. If you want to post a HTML form to a site, that's a simple request. So all those new requests that are sending JSON aren't considered simple. HTML forms don't support JSON, and so they trigger that pre-flight anytime that you're trying to pass JSON as the body of a request. So that led to that false sense of security because they're using JSON, so it's going to trigger that CORS pre-flight and they're going to be protected. Problem is, CORS is not a security specification. Any added security that may have come about because of CORS was incidental. They spell out in the specification itself that requests still need to be protected from CSRF attacks because it doesn't provide any protection from attacks. It's just a specification for exchanging data between sites. So if we take a look, if we jump back to our buddy Bob, and we're still on the site. It's the site that the developers upgraded to, that they're passing JSON as a body. But our attacker got a little bit, or did a little research and wisened up a little bit, found a way to exploit the site as a whole. So he redid his site. Got a new cool Pop-Tart cat flying through space. But we can see that the attack still succeeded, and Bob's name this time was changed to CSRF JSON. But if we look at what happened in Bob's browser, it was a lot more involved, and that Bob visited notevil.com, and it kind of sent him through a series of requests that ultimately ended with Bob once again submitting data to change his name. Once again, that's essentially the premise of a CSRF attack. This is Bob performing these actions. It boils down to something I read in a book long ago. Somebody made the statement that computers are inherently stupid. They do exactly what they're told. And so in this case, the notevil.com is telling Bob's browser to perform this request, and Bob's browser is just performing the request because that's how the internet works. You define a request that's made, whether it's a GET or a POST, and the browser makes the request, issues the request. They're not smart. They don't think about what they're actually doing. They just do what they're told. So if we step through what actually happened in that request and how the CORS pre-flight was just completely ignored or bypassed, we can see it's a little bit more involved, but you're still vulnerable if you're using JSON as the body of your request for the body of your requests. So we look back to just the standard Bob setup that we've had. Bob logs into safe.com. Safe.com sets a cookie. Bob goes to notevil.com. Now, on notevil.com, there's a couple different options. You can either have a JavaScript or a script setup that creates an embedded object, an embedded Flash object that goes onto the page, or if you want to be a little bit more malicious or sneaky, you can base64 encode an embedded object and stick it on the page. So when Bob browses to that page, once again, or Bob browses to that page, and that script is executed. In this case, Bob's browser now tries to access the object that's on notevil.com. It's this Flash object, test.swf. And there's a couple parameters that are being sent to this Flash object, such as the endpoint that we're ultimately targeting, what type of request we're going for. In this instance, we're doing a post, what the content type is. We're exploiting a JSON request, and then the actual data. And then we have this redirect URL down here. And both this Flash object and this redirect object reside on notevil.com. And so this Flash object then redirects Bob to the redirect, or sends Bob to the redirect page. And the redirect page takes a little bit of information, has the endpoint, but if we look at the request that Bob's browser actually sent, the content type has been changed to application JSON, because Flash has the capability of crafting raw HTTP requests. And in the body of the request, there's the actual body that's going to be sent. It's this JSON object with the name that's being changed. And so this redirect page is literally one line of PHP. All it does is it takes the endpoint that's provided as a parameter and does a 307 redirect to that endpoint. So we get the 307 redirect with the new location that was provided as the endpoint there, and then we get the ultimate or the final request being sent, which is a post to safe.com to the user endpoint with the actual JSON body and the content type being JSON. And since it's coming from Bob's browser, it includes Bob's session for safe.com. So it's kind of a hairy mess to make that way, or to get around to do that CSRF attack. But it bypasses that CORS pre-flight, makes it so that the request will succeed and it's structured exactly how it's supposed to be accepted by the vulnerable site. So the main reason Flash was used is Flash, they came up with what's referred to as the Flash cross-domain policy, and they put that out several years ago, and it was before CORS came about. And the 307 was used because it maintains the structure of the request that came in when it redirects it. Or if you use like a 302, it's going to do a GET initially. And so it won't do post, it'll just change whatever request came in to be a GET. And so once again, active and passive protections do work. So we go back and we look here, we'll take a look at that real quick because we're running out of time. Bob's browsers, or Bob's developers, once again, update their website. So Bob logs back in, goes back to notevil.com. There's the whole series of requests again, and Bob's username doesn't get changed. The main difference being that when Bob issues a request, there's now a CSRF header that's being sent with all of Bob's requests. So maybe the developers decided to maintain the integrity of the object that was being passed around, so they didn't want to include it as a parameter in the object, so they passed it as a header. But once again, the token protected the request because the attacker doesn't know what that token is. They have no way to retrieve that token and include it in their requests, and so their requests fail. When they send their requests, request initiating from the attacker, there's no token, so they fail with an invalid CSRF token. So some final thoughts for you guys. I'll just put these up really quick here. Nope, too quick. So every state changing request on an application should be protected, or should have some form of CSRF protection, whether it be active for sensitive actions such as transferring money, things of that nature, or passive, just including a token or a header with every request that is sent. A lot of frameworks out there do include some form of CSRF protection, but all too often I see developers that just, forget something as simple as just turning CSRF-Protection on in a config file, so they're not actually taking advantage of the protection that is provided. So leave you with the links if you want to learn more. You can go look up stuff there. Otherwise, I'll be hanging around for a little bit. You're welcome to come ask me questions, and go ahead and run off to lunch. Just right out those doors. Thanks for coming.